Hello all. Welcome to the lecture series on the course Deep Learning Techniques in Medicine. The Module 1 covers the introduction to deep learning. We have already seen about the neurons, the perceptrons, multilayer perceptrons, and the support vector machines in this lecture series. And this video covers the concepts about logistic regression and the limitations of the linear neurons. What are the limitations that we will be facing? I am Dr. Sivaranjini, Assistant Professor in the Department of Biomedical Engineering, SRMISD, Katangalattur. Moving into the lecture, if we can see that if the output is either a yes or no, how do we predict the probability? Okay, so there comes the picture of a logistic regression network. So what this logistic regression is? So this logistic regression is a linear classification model that predicts the probability of the binary class using a sigmoidal activation function. So in short, we can say that it uses a linear equation, uses a sigmoidal activation function, and then gives you the probability like to which class it belongs to. So it is used for a binary classification where the output lies between 0 and 1. Okay, so it is interpretable as the probability of a class it belongs to. So what is the logistic regression using? It's still using a linear neuron along with a nonlinear activation function which differentiates itself from a multilayer perceptron or an SVM or a perceptron, simple perceptron. Okay, so the linear equation is T equal to W into X plus B, where W are the weights and X is the inputs. So the equation can be expanded as W1 X1 plus W2 X2 plus W3 X3, and it goes on till Wn Xn plus B. B will be the bias term. So it is the same linear part as a perceptron or an SVM or a linear regression, right? So what the difference here is like the activation function and not the linear part, right? So the weighted, it uses the same weighted sum as a perceptron with a combination of the inputs, weights, and the bias, right? So what is this sigmoidal activation function that is used, or the logistic activation function that is used in a logistic regression, which makes a difference with the other networks, right? So this sigmoidal activation function, sigma of t is equal to 1 by 1 plus e power minus t, where t is the input, right? Sigma gives you the sigmoidal activation function, sigma of t, right? So this sigmoidal activation function, it takes any real numbers for the t value to be minus infinity to plus infinity, and then it squashes its range to the 0 and 1. Okay, so the output range, even though the value of t which is obtained from the hidden layers ranges from minus infinity to plus infinity, it squashes the values to the range from 0 to 1. Okay, so why is it needed? Why do you need to squash the output from minus infinity to plus infinity to 0, 1, right? So z alone is unbounded and it can have any value. That's what I told you. It ranges from minus infinity to plus infinity. But the classification task needs to be a bounded one, right? So we need some interpretations from the output. So sigmoidal activation function gives you that interpretation, right? So what are the properties of this sigmoidal function? So the properties are the output range is from 0 and 1. Never actually reaches exactly 0 or 1, but it only approaches asymptomatically, right? So the next property will be smooth and differentiable, which is necessary for gradient based learning. Okay, what is this gradient based learning? Is like it tells you like how much or how much derivatives are used for changing the weights. How much is the change in the weights in each and every training phase. Okay, so we will be seeing about this gradient based learnings in the upcoming lectures. So the other property is monotonic increasing. Monotonically increasing means larger t-values always gives larger probabilities and no reversals and keeps the interpretation consistent. Okay, so how are we going to do that interpretation? Right, so we do have the sigmoidal activation function curve. So what the sigmoidal activation function curve gives us, right? It is a kind of a S-shaped curve, right? So what this curve gives you? So you can see that the value of t when it goes on in the negative side, right? So this is the value of t at 0. When the t goes in the negative side, the curve flattens near the 0, okay? The t goes on in the negative side and the curve flattens here. And when the value of t goes on increasing or it goes on in the positive side, the curve flattens near 1. Okay, the curve flattens near 1. So at what happens at when t is equal to 0? So this is the steepest region. The change or the turnover happens here. Okay, so the output is exactly at 0.5. Between 0.4 and 6, it is 0.5. This is the probability interpretation. Okay, the output is the probability of belonging to class 1 or class 0. Okay, usually this point is called as the threshold, which will be used for classification. So how can we summarize this as? The steep middle region is where the model is most decisive. Decisive in the sense where we are taking the decision. And the small changes in Z causes large changes in probability. And the flat tail means, the flat tails mean the model is already very confident and further changes in Z barely move the probability. This is also the root of the vanishing gradient problem. Okay, so what did I tell you about the vanishing gradient problem? We already saw that vanishing gradient problem is nothing but how much difference, how much weight change difference from one step to the next step, how much weights has to change. That becomes the gradient problem. And the vanishing gradient problem is a major issue that most of the networks face. We will be seeing about it in the upcoming lectures. So the output will be the output interpretation will be through a threshold, which will be used for classification. So it is a hard class decision where the output is greater than 0.5, it belongs to class 1. And the output less than 0.5, it belongs to class 2. So the decision rule in logistic regression relies on computing the probability. After computing the probability, what happens? Your y will be the predicted output, y cap, right? Y cap, when it is 1, it says that it belongs to, it belongs to the class 1 or class 0 based upon the sigmoidal activation function output. So when sigmoidal offset is greater than or equal to 0.5, it belongs to class 1. And if it is less than 0.5, it belongs to class 0. So this creates a linear decision boundary like Wx plus b is equal to 0. Hence, we can see that the logistic regression is still a linear classifier. It is not a non-linear classifier. Shall we see about a small disease prediction example? Take for granted that the patient's symptoms are the results. Okay. Example, the tumor markers or the blood values, the CBC values, which are given as inputs. Okay. They are combined into Z through the weights. When they are combined, the combined weights are combined in the sense when we are trying to multiply their inputs. Inputs are the tumor markers or the blood values, the test results, right? When we are trying to multiply or combine them with the weights to obtain the set. Okay, this set, the value in the hidden layer is passed into through a sigmoidal activation function, which gives you an output saying, it can be, say the value of the sigmoidal activation function is 0.9, right? So the interpretation which can give is like 90% the probability that the patient has a disease, right? So when it is 0.9, it is very close to 1, because since it is saying that it is greater than 0.5, it is very close to 1. So it reaches to the class 1, and since the patient has a disease, so it comes as a result as 0.9 is very close to 1. So it has the patient, it says that the patient has a disease, right? So and important point to note is like the patient is likely to have a disease. That is what will be the interpretation from any neural network. But in medical diagnosis, here the threshold doesn't need to be like 0.5. You don't need to set up a hard threshold value. So the threshold value can be lowered so that you are not missing any diseased cases, right? So the false negative cases are the costlier ones that can cause an alarm in a medical diagnosis. What are these false negatives? Is like you are trying to tell a subject who is healthy as a diseased one. Okay, so you are telling that you are trying to analyze and say that a diseased person is a healthy person, so that the treatment is not given to them, right? So the treatments are getting delayed, and that becomes a false negative, which is actually a very costly issue in a medical diagnosis field. So it's called as a false alarm, and this real design decision is not suitable for a medical diagnosis, right? So on a short, we have seen that logistic regressions are still a linear classifier utilizing a sigmoidal activation function. So what is the loss function that is used? Loss function which is computed at the last part of the network at the output layer. So unlike a perceptron, which is a non-smooth loss, logistic regression uses a smooth convex loss. So what is a smooth convex loss? How it is calculated for one data point. Loss of y, which is a actual label. Okay, so this is the actual label, and y cap becomes the predicted probability. So this loss between the actual label and the predicted probability is given as minus y into log of y cap plus 1 minus y into log of 1 minus y cap. Right? So this is also called as the log loss or the binary cross entropy loss. Right? So why this loss is important? Why this loss is used in a logistic regression? It penalizes the confident wrong predictions heavily. Penalizes in the sense it gives a very heavy it gives you a very bad output. Okay, right? So this the logs function steep curve near 0 is what creates this heavy penalty. Okay, the curve becomes the heavy penalty. So this enables the larger gradient based optimization. So this loss will be giving you a larger, will be enabling you with a gradient larger, enables gradient based optimization. So being so what this gradient based optimization is like, being differentiable everywhere means we can compute the difference, the gradient change or the updates in the weights through the gradient descent algorithms. Unlike the perceptron step loss function, this loss function is not so like the step loss function that is used in the perceptron. So this loss will be a convex loss which guarantees you a global minimum, no risk of getting stuck in the local minima during training, since the loss surface has exactly only one lowest point. So what are the limitations of this logistic regression? Here we have a linear decision boundary and it is not able to solve non-linearly separable problems, which are somewhat similar to the problems that are being faced by a perceptron, a simple perceptron. Even though we have a nonlinear activation function, the linear decision boundary still remains linear. The decision boundary remains still linear. So also we need feature engineering or kernelization to handle nonlinear patterns. We must manually transform the inputs or use some kernel tricks so that the model can discover these transformations by itself. Right. So a straight line boundary cannot classify complex real world data such as the images, speech, handwriting, and medical images. So what are the limitations of the linear neurons that are being utilized in the perceptrons or multi-layer perceptrons or SVM or a logistic regression, right? So first limitation, as we already saw, we can only have a separate data. We can only separate the data using a hyperplane, and it works well for linear separable data and it does not work for complex patterns. Second limitation is like non-linearly separable patterns cannot be solved with these networks, and no straight line, where the no straight line can separate the classes. So the third limitation is like a composition of linear function is still a linear function where depth alone does not increase the learning part. So you go on increasing the depth or the number of layers into a network does not give you a better learning part. Multiple linear layers without nonlinear activation function is still a linear model. So what is the fourth limitation? Okay. So these linear neurons operate directly on input features. Input features in the sense raw input data. They cannot learn the hierarchical patterns. Hierarchical patterns, what are the hierarchical patterns? We have the edges, shapes, and the objects, which is like from the edges, we derive the shapes, from the shapes, we derive the objects. And this follows from the simple to the complex patterns, right? So technically speaking, we are using a single weighted sum or plus an activation. Okay, so this activation, this is the main portion of a perceptron. This has no mechanism to combine the low level patterns into the higher level patterns. That combination requires stacked layers, which are being used in the multi-layer perceptrons. So the next limitation will be, we already know that it uses a nonlinear sigmoidal activation function, but still the decision boundary remains linear. Okay, so we conclude that the linear neurons require well-designed input features. They are not able to give or derive the features that are required for the required task. So they cannot automatically discover complex representations. Okay. So we need the human designer to fix for it, and there is no learned transformation of the raw input space, unlike the deep networks where hidden layers learn from their own feature representations through backpropagation. So the backpropagation training algorithm is used where they learn to correct their errors and conclude to some point, right? So in this lecture, we have seen about how logistic regression can be used, and what kind of loss functions are used for the logistic regression, what is the activation function used, and what are the limitations of the networks that use linear neurons, right? So to conclude, we have all these linear neurons. So the need is like, we need neural networks, and from the neural networks we need deep learning networks, right? So the more complex the data is, we need models that learn the hierarchical non-linear representations automatically, not the handcrafted features. Okay, this is precisely what stacking layers with non-linear activation achieves, right? Removing the need of manual feature engineering. We remove the need for manual feature engineering. So to conclude, we say that the logistic regression is a powerful method for binary classification task, but it is insufficient for high level complex problems, right? So in the next video, we will be seeing about the activation functions and how these activation functions are used. Okay, thank you.